Okay, I just started recording the session. It's about 2 minutes to 6. My name is Daryl. Let's see, can we get confirmation? If I can get someone to confirm that they can hear me or that they are listening in by typing in a message, that'd be great. Thank you. Wonderful. So I have 5:59, so I'm just going to do a brief explanation of what I'm going to do for this review. I went through and quickly did a brief summary with the professor's notes and with what I read in the book. And so I'm going to show you a PowerPoint outline very briefly that kind of will just do a very simple walkthrough of everything that kind of was in the book and any kind of meaty portions. So this section is not meant to go into nitty-gritty stuff. I'm only hoping this will take like maybe half an hour at the most. I hope to do some brief examples and that you should be able to see on your screen. There will be blank spots on the PowerPoint that I can draw in and fill in for you. But I'll try to make sure that what the professor told me were some critical spots. I'll stop and hopefully I can see on the screen, if someone has a question or not, and I won't, miss it and have gone on too quickly. But this PowerPoint is not meant to take very long. So by the end of the PowerPoint, you can hopefully get an idea of, what maybe you should read up on more or what you should take notes on. It's not meant also for you to take notes from. I mean, you can. You should be able to write fast enough, but it's also meant just kind of give you an idea of what the topics are, again, as a full review. Hi, electronic 120? Yeah. Okay. So I was also told that this exam was open notes. And then for the student in the class, there's some people online, so I'll be referring to kind of like online scenarios. So I'm not going crazy. I was told this exam was open notes, so that should help you quite a bit. And let me see, I can't really see if anyone has questions for this. And so this should make things a lot easier for you as you take your test. If it's open book, I'm going to probably suggest certain things that you should definitely actually have in your notes that maybe you didn't want to take the time to in class to write down or jot down. She was giving it to you, so that way we can go through it. So as you can see, we're just going to go very quickly through all the topics. And this is not meant to like write down or anything. It's going to give you an idea, again, of what you should know and maybe what you miss in your class sessions. So quickly, just going through chapter 1, we have the cosmic address. If you look at the PowerPoint, you can see it's the smallest to largest. U, Earth, solar system, Milky Way, local group, superlocal cluster, universe. I suggest you know the sizes of each. You might get a little bit confused with like Milky Way, local group, the latter ones, not necessarily, the ones in the solar system and Milky Way, but some of the latter ones. Just make sure you know the difference. You need to know your astronomical distances. So astronomy. You should know that AU is the unit of length when dealing with space distance, and it's the Earth's average distance. The Earth, of course, is an elliptic around the sun in our solar system, so 1 AU is actually the Earth's average distance. LY is a light year. It's the distance light travels in 1 year. The idea you should take from this is that we're actually looking back in time. When we look back into our universe, because light is traveling over vast distances to us, hence, millions of years have gone by the time light has reached us. I put a little blurb here for lots of vocab. I am not going to tell you what exactly you should know. There's lots of vocab in this book, right? So some are very nicely black bold words if you have the book and have read the book a little bit. If you're just taking it from notes, I think she does a pretty good job too of like underlining, I think, from what I read from her notes about certain vocab. So there are vocab. If you're more from the notes side of things, just make sure we'll talk about it more maybe. Just make sure you know certain vocab as you go through, just so you know what words mean. I was also told there's no unit conversions on this test. So there's going to be math, but not really any kind of unit conversion. So you should know how to convert a distance to, like velocity distance and stuff like that. It's going to be more conceptual, but there is going to be 1 or 2 or 3 questions that deal directly with math. You got to do your universe history. You got your Big Bang theory, right? The idea that everything started at one point in our massive space. You need to know kind of how the star of stars go. You have gravity strong enough to bring all basic elements together. Your basic elements, you should know, are hydrogen and helium, and it's because of, the fusion of stars that you actually get your other elements that are more massive in size due to the gravity and compression. A section was called Earth in Space. It was your rotation. You should know that we go west to east. We go counterclockwise. You should know that we rotate in the elliptic plane, and Earth is on its hill. We'll talk about that a little bit later. If you two in class have any questions, you can stop too. I'm trying to do both online and in class. Round sun. We're going around the sun also in a counterclockwise elliptic direction. You should know the raisin cake analogy. The idea that even though everything is moving away from us, we're actually all moving away at the same speed. Not necessarily the same speed, but we're all the same distance apart. So the idea is that even if you take time and you calculate at times in the universe, if you were to look at this raisin cake analogy, we are actually all the same distance apart no matter where you are in our space. So if we went to the far reaches of our universe, and you were there, from that point, and you measured the distances between maybe local clusters or anything, you would notice the same distance apart. So the fact that from visual measurements of light, it's kind of an interesting idea. Chapter 2 talks about the universe from Earth, and this is constellations, the celestial sphere here. I'm going to do a quick drawing for you. And this is the idea that before we could actually figure out whether or not the Earth was going around the sun or the Earth was the center of our universe, the ancient Greeks, of course, made this idea that there's this idea that Earth was the center of our solar system, and we have this very basic plane, which is just the Earth's equator magnitude on outside of a certain distance. I don't know how big these spheres are in terms of radius from the center of our Earth to the outer edge of the celestial sphere. The key thing to take away, though, is that on this specific drawing, we have this other plane called the ecliptic plane, which is it's from our Earth-centered position of this sphere. It's actually going to be the sun's movement of travel around the Earth. However, because we're actually moving around the sun in free fall, it's really the Earth's movement around the sun. However, because we're using this relative visual perspective of what's going on, that's what the ecliptic plane is. You should probably also remember what the angle is between the equator and the ecliptic plane. It's 23.5 degrees. And of course, you have your north and south poles. And I'll just also briefly draw. Here we're going from, we're rotating in a counterclockwise direction. When it comes to later visualizations about understanding horizons and maybe how we see stars at a given point in time, we just have to remember that if we're anywhere on top of the Earth, within a given distance, you can pretty much cut your sphere in half. When you cut your sphere in half, you can then look outwards onto the sphere and you can see certain stars within the time of the year, the time of day. The study guide that I am using, the PowerPoint you mean, Emmanuel? It should be. I'm just not sure how fast it goes through IIT's like servers. I think we give it to someone else to put online, and then it's up to them to like okay it. So unfortunately, I know your test is tomorrow, so I'm not exactly sure how fast it's going to be on. As soon as I'm done tonight, I'll send an email out to my boss and ask if we can get it up there as quickly as possible. Again, unfortunately, I'm not sure how quick it's going to go. Okay, back to the PowerPoint. North-south equator ecliptic sun's annual path. Right, the ecliptic, again, is the sun's annual path, which is that at an angle if we're using the Earth as the center. You should know just kind of, I'm just going through very brief topics. So Milky Way, you should know the local sky. The local sky is the hemisphere that was drawn, that I also drew on that previous picture for you, which is here. You know, that's cutting, wherever you are located on Earth, you can almost go a 90-degree direction, left or right, or counterclockwise or clockwise, and that will be your horizon. And there are just some brief things you should know. You should know kind of just some of the vocab, like zenith, which is the top portion. You should know that within certain natural boundaries, you should be able to see all the way from counterclockwise or clockwise, depending on like if you have mountains or something. And you should know the angular size. So you should know that we measure things with a degree, and then we measure smaller things with 60 arc minutes and 60 arc seconds to get very small angles, which the ancient Greeks were not able to do. Stars rise and set. You have your circumpolar. Stars remain perpendicular above horizon. This comes from the fact that if we go back to this drawing, I'm drawing in a different color. This section you cannot see at all with our man or woman right there. So if you were to try to look at the other side of the Earth, you cannot see the other side of the Earth at all. However, for circumpolar, we'll even use this right here. Any star constellations you see actually above, according to my drawing, above this bottom green line, you will always see all the time in the north. Because no matter what angle, no matter how many turns you go, you're always going to see from the edge of your horizon. For those online, you can always see from the edge of your horizon all the way around back here. So anything above this line, because remember these are all stars up above here, you can see. Now if we go below that, using red to go below, if we go below that, you'll notice that as I draw these dashes, once we turn a certain amount of time in a day, you will not see the same constellations anymore. You're only going to see them for a section of your day. And those are not circumpolar. Remember, circumpolar is only anything up here. And again, if you want to continue drawing it, you're actually going to get to a point where you're not going to see any types of stars whatsoever if you're at a given section on the planet. Okay? Your constellations with latitude. That kind of just goes back to the picture saying, you know, your edges of your horizon are going to change depending on where you are with latitude. So you should know what latitude means and longitude. So depending on where you are with latitude, your edges of your horizons will change, and you'll actually be able to have certain, different types of almost circumpolar stars. You should probably see most of the north. You will see all the north ones, I believe the book was saying. So, like, depending on where you are on the planet, you'll be able to change that. Causes seasons. This is another important one. I believe it was pretty well discussed in your notes. As you can read, the sun's rays are at different angles. I believe her notes went over the fact that when you're at different angles, so steep or shallow, the way it just enters the Earth's atmosphere, the way it actually will penetrate, because we have a curved ball almost in space, is that your rays will hit the land, will hit the land masses at different angles, and you'll get a higher intensity per unit area. Once again, higher intensity per unit area. And that's described, as you can see, right here. This is not caused by the distance from the sun, but just the tilt, because once again, you get summer and winters by intensity per area, the number of 1 meter squared of sun's rays for 1 meter squared for summer, with this as your foundation. And then if we go to what our winter seasons would be, you get 1 meter squared of rays actually giving you an intensity of 2.5 meters squared area. So it's more with the tilt and not exactly how far away you are from the sun. And then you have your solstices and equinoxes, and here it's briefly explained. These days, I believe the book mentioned, were subject to more like kind of like a cutting of the year down. One orbit around the sun was broken down equally. But the most important things you probably take away is, of course, read again into your notes about this, but also that this is what's happening during these times. So when we're in summer, even though it's in June, and if you're from Chicago or from anywhere in the upper North of America, we don't feel things until August, or we don't feel heat until August. But the North Hemisphere is tipped most directly on June 21st, and then it kind of continues from there. The south is the south hemisphere tipped most away. Sorry, this should be north because it's the same hemisphere. So north is tipped most directly, and then the north is tipped most away. Sorry about that. And then these are the two times when the Earth is technically, when we're looking at the ball, is technically almost, even though it's still at an angle, as it travels around the sun, we're actually changing the hemisphere position just slightly, so that it will be in a vertical position at these 2 days approximately. And then as a quick note, there's more land in the northern hemisphere based on how the Earth is positioned in space, and there's more water in the southern hemisphere, so water requires more energy or heat to warm up, where basic land geology does not. And therefore, we actually will have more extreme weather because the heat of the rays is absorbed in the water. So, the moon, I heard the moon was slightly an issue, so I'm not sure if anyone in class or online had any problems with this. Did you two have any problems with the moon phases or anything? No? Okay. Anyone online have any problems with the moons? There's a lot to be covered. Could you explain further? What do you mean? What do you mean by there's a lot to be covered with the moons? Are you able to narrow it down at all? Here you have the phases and times in your notes. It's going to save you a lot of time and effort because it's an open note test, right? So if you have, I don't know what she drew for you. What she drew for you most? But what I'm basically saying is, instead of memorizing it, write it down. Go back through your notes, make sure it's there. Does she have online viewing sessions? IIP? Just the notes are online? Okay. So make sure you go and write those down, because that's going to save you at least probably 4 or 5 questions, which I hope to get to in about 12 minutes. Yeah, I mean, there is a lot. I was looking at the diagram now, and you have at least maybe maybe 8 concepts you could go through at any given time. So I guess for Maxwell, I'm just going to say them out briefly. You probably should know, what's waxing and waning, right? You should know the difference between crescent, gibbous, and then each quarter of the moon, right? So that you waxing, waning, gibbous, or crescent, and you should know kind of like the quarters, right? New moon, third quarter, full, first quarter. You should also know, this is why I'm telling you to write it down or at least find it in the notes, is because you should really know the times too, because it comes back to the fact that when you look at your horizon, when you do the half sphere, the moon and the sun are actually in the sky at the same time. And so we'll see on some of the questions later that there can be kind of, you should know the time. So like I said, if you can just write it down, it's an open note test. It'll save your brain some space to remember stuff. Okay, so you should know the ellipses, right? You have lunar. The lunar is, I'm trying to think, how did I do this? Okay, I put the farthest object away first. So in a lunar, if you're going from the center of our solar system, it goes sun, earth, moon. That's a lunar eclipse, where the earth's shadow is on the moon. Once again, I did, you can either go farthest to nearest, being the center of our solar system is the sun. And then for solar, you have the sun, moon, and earth, where the moon's shadow is on the earth. Conditions, if you were looking at the moon, like with that diagram for the phases of the moon, it must be full or new. Full being the lunar, and a new moon being the solar. And then the book also maybe goes into this idea of nodes. And all that is saying is that we're not all on the direct same plane. The moon is going to be, if you're looking at the ecliptic or the celestial sphere, the moon is also above our equator or below our equator. And that's kind of what they're just saying, is that in the ecliptic plane, they must be in the same plane for this to happen. And then you have your lunar. You should know these words. I'm afraid I'm going to botch it up. Prenumba, partially blocked sunlight. Umbra, fully blocked sunlight. You should also know the difference between these three, a total lunar, a partial, and a prenumbal, because your book, she could easily ask you a question based upon these, because the way the light of either, the way the light from the sun hits the earth or hits the moon, you actually have partial shadows, full shadows, or a combination of the two. So that's why I put these here for you all, is because okay, I'm going to briefly draw it just because I'm not describing it very well. So you have your sun. It's just an idea, because it can ask you quite a number of different things. In this, okay. So here is our Earth. And this will be, I don't know which one I'm drawing. So let's say your moon is there, or your moon is here, right? What happens is your rays, your sun rays, hit the Earth. However, you have this, you have a, that's the one there. Okay, so it's a little difficult for For solar, you're actually going to have this section where the shadow, might not reach the surface of the Earth. And I looked through her notes and she didn't go over this, so I just want to briefly mention it. So you have like several shadows. So for the solar, if you're in this region, it's total unless this doesn't reach, or it has to reach to get total. But if on the other side of the diagram, as I'm briefly over here, you actually will hit. Now that's this is. So for lunar, the Earth projects itself onto the moon, but there's this kind of gap here. And then you're also going to get direct penetration. So look through your notes. If anyone has any questions on this at the end, I can gladly go through it a little bit more, because I don't think I saw it, so I added it just in case. You should know the totality. Kind of a cool thing is that the partial phases of the moon will show the curvature of the Earth. So it's kind of a neat thing from the history of the astronomy stuff. Like people have been debating, how is the Earth round, flat, cylindrical, and all that. So it's kind of I think it's a cool thing that there's a small proof right there. This is kind of another neat thing that might show up, is that the red tone of the moon is actually the sunrise and sunsets all at once happening on Earth during a lunar eclipse, because it aligns just perfectly. So it's a total lunar eclipse, and it aligns just perfectly so that the light from the sun is actually at such a shallow angle to the Earth's atmosphere that all you see is kind of the red of the sun. You don't get any scattering or anything to give you the other colors. You just get that red tone. So that's kind of cool. So know your solars, total, angular, partial. Follows from moon on how shadow falls. Follows from moon on how shadow falls. That was just, I think, what I was explaining earlier about your light is actually changed a little bit over the course of your lunar or solar. Apparent retrograde motion. This one was kind of cool too. Did she draw any diagrams for retrograde motion? Anyone online want to add? Because I'm going to draw really quickly anyway, but. Okay. I got to get this right the first time around. So remember, retrograde motion was the fact that as a planet, as you were viewing it from the Earth, was going sort of around the celestial sphere, because on our sphere we see a planet, and we notice, right, that over here it's actually doing kind of this weird going backwards, and then it continues along its path in the sky. So retrograde just means it's going backwards, right? Because going backwards, and then it resumes its path along this sky. Well, an easy way to understand this, just briefly, is if the planet Earth is on the bottom here, and it's kind of moving at its nice yearly orbit, we're viewing. planet itself is where the green arrow intersects the red line. And as the Earth moves, you see it. Oops, what's going on? As you're visually watching this, there's a point in time where, as we visually see it from Earth, even though the planet itself is moving along its own elliptic, at one point in time, as we observe it, the planet actually looks from our perspective as if it went backwards. Okay. They could not accept this for your history portion. They could not accept this due to stellar parallax. We are at different sides of our orbit for different views. Celestial sphere, you should be closer to parts of the Earth. So this is just kind of some of the reasons why they didn't accept what they were observing a little bit. Because remember, they put the Earth as the center of a big sphere, and they felt that they should be closer to different parts of that sphere if Earth was moving. However, we know that because space is so vast that the small distances we travel and cover do not really bring us that much closer to any of the stars. So they could have had two answers. They chose the second one, and because the minds of the Greeks at that time could not imagine the distances that were being discussed. Okay. Chapter 3, you got your history, ancient roots. These are just brief mentions. They were able to, in the tropical rainforest, you could do rainfall in the moon cycle. You could measure of time and days. So the moon is month. You have your years and seasons. You have your day. There were several structures that were talked, I think, about briefly that kind of were built almost as a way to measure where the sun was and kind of measure how seasons worked. You have your overall Greek science. They debated. They included mathematics, and they were heavily on their observations. So anything that didn't go over observations, they kind of threw out because it was supernatural, or they relied more on what they observed. Here's just a brief idea of how, for the history, it moved from Aristotle to Europe. So Aristotle knew Alexander, or was a tutor. Alexander built the city of Alexandria library because of Aristotle. And so now we have this huge collection of scholarly resources. This was destroyed, and the few surviving works that they could decrypt, went to Baghdad, went to the House of Wisdom in Baghdad. Baghdad, of course, is closer to India, so the Indian scholars were able to get information from the House of Wisdom or Baghdad. And then because India is one step closer to the Chinese scholars were able to share their wisdom on astronomy and what they observed. However, Baghdad, the info in Baghdad spread out to what was known as the Byzantine Empire. However, when this was destroyed, like in kind of most wars, most of the scholarly people move to a different portion of the world. You can even look at that in the recent world wars, right? A lot of the European scholars moved to America. America had a lot of breakthroughs during that time. It was the same thing with the European Renaissance. A lot of these scholars from the Byzantine Empire moved to Europe, and it started up this new era. You should know what the geocentric and Ptolemaic models are. I broke down the Copernican revolution. Sorry. He brought into the idea that there's heavy math, meaning there's more than just observations, there's more than just simple calculations. He brought in a much more algebra and heavy math that kind of was brought from the Baghdad era when everything was when they developed algebra and developed more sophisticated mathematics. He also moved the sun to the center, but he still kept the circles, which was wrong. Tycho, he developed more accurate naked eye data. He fully devoted his life to get the best naked eye data that could be developed because we haven't had the telescope yet. He also, let's see here, Earth, middle, other planets, orbit, sun. So what he did though, is he kept the Earth at the middle, and he decided to have the planets orbit the sun. So now we have the sun orbiting the Earth, but now the other planets orbit the sun. So we're getting a little bit closer to what recent, modern day observations are telling us. And then Kepler took all his data, the more accurate naked eye data, and he said, well, I can't deal with this data that my advisor found for me. And he developed even more advanced mathematics, and he was able to change the circles to ellipses, and his data became extremely accurate. I have draw ellipse here, so you should know just very basic. Idea of ellipse, right? So ellipse is not a circle. You have two foci. One is a focus, but the plural is foci. You have your semi-minor axis, and then you have your semi-major. This is important because when he was developing the axis for this, he decided to place the sun, Kepler, he decided to place the sun at one of these, and he left the other one blank. And then we have now the mathematics that can go into this, where you have to use more advanced mathematics, so things are not as simple as a circle. You don't have pure radii anymore. You have different distances using two foci, using the foci. You should know the three laws of Kepler. You should know the vocab, perihelion, aphelion. You should also know this idea that the period of the orbit squared is equal to the distance that it is away, cubed. And that this idea that we have elliptical orbits, and the fact that depending on where you are away from the sun will give you a faster movement around the sun, gave rise to the idea that there must be forces involved. And this was kind of the first idea that there was a force between major between a star and a planet, or stars in general. Then Galileo came along, and he took what was a toy, the telescope, and made it an instrument for science. There were three objections. I don't think you need to know them. There were three major ones that, at least when I read in the book he was using. He answered all these three, but then he also made two new observations, which are important. You should probably know. You should know these two, because I know this one, I believe, was used on a previous test. He observed moons around Jupiter, which means that moons not only orbited the central of the solar system. So if we have the Earth at the center, we thought, well, since we have a moon orbiting us, we should be at the center. But now that he observed that there were moons orbiting around other planets, that was just kind of another say, okay, well, that's not the only reason we should be at the center of the universe. And then his biggest observation was the phases of Venus, kind of like the phases of the moon. If Venus only stayed around the Earth, therefore, when the sun rotated, we would only ever see certain crescents, or you would see gibbous or crescents. You wouldn't actually see no gibbous, you'd just see the crescents. However, you observed all the phases of Venus. You saw like what a moon went through. You saw the new, you saw the full, you saw new moon, you saw quarters, you saw the waning and waxing of light that was on Venus. So Isaac Newton came into play. He came up with F equals ma, which is really the change in momentum. You got your 3 laws here. You should know those. Know the equation for angular momentum, so that's one of the equations you should know. Astronomy review?
Yeah.
Okay. You should know what the equation is. It's one of the calculations you might do. And then here we jump into energy, so you have your kinetic, radiative, potential. You should know that energy is conserved. Energy, what it means by having energy conserved is that you can go from 2 of these to a third, or 1 to 2, or have all 3 present, but the total energy measured in your system and the universe, so the total energy in the universe has to stay the same. And then this is just bringing in that mass itself, mc squared. Mass can be converted to energy. You should know what Newton's book, Universal, I misspelled it, Universal Law of Gravitation, obviously. You should probably know by now what it means to say inversely proportional when something's proportional. So when I say strength is proportional, that means it's the numerator to numerator comparison. You should know that something inversely proportional is numerator equals 1 over the denominator. So 1 over a number is inversely proportional. So this is your basic m1, m2 over 4 pi r squared, or the distance squared. That would go here. I was reading about escape velocity, and you should know that we're actually falling in space. Yes, there is forces on us in space, but those forces, but there's nothing in between, in a sense, so that's why we're falling in space. So if we're close enough, we fall back down to the planet for escape velocity. You should know the tidal effects from the moon, sun, and tidal friction, or some words that were mentioned. And then to the gentleman that just entered the room, this PowerPoint is just kind of a brief overview. It's not meant to take notes from. It's kind of like, oh, this section I don't remember. Let me write down that section. Okay. So then we get into our last chapter. You have your light and matter. What is light? You have everything that deals with light. We're dealing with a spectrum now, but it's only in the visual spectrum. You have light and matter, so you have emission, absorption, transmission, reflection, scattering. We go into the particle or wave, but we're only dealing with the wave nature of light, it seems. So we know that the wavelength, here's your other equation you got to know, wavelength times frequency equals speed. And we know, since we're dealing with light, that speed of something is always going to be 3.0 e to the 8th. It just means 3.0 times 10 to the 8th meters per second. Light is an electromagnetic wave, and that's only in this spectrum, 400 nanometers to 700 nanometers. Apart from small portion. Right, so there's a large, extremely large spectrum. I believe it was given to you in notes, or the notes are online, as I was told. Make sure you have it for your test, just in case something comes up. That way you're going to have a table or graph you can look at. You don't have to memorize or say, oh, I forgot this. Let's see if anyone online had anything. Nope. Everyone online doing okay? Thanks, Maxwell. Okay. Oh, 2 more seconds. So you need to know the structure of matter, and you talked about the atoms, protons, neutrons, electrons. So these are all, except for the electrons, are all in the nucleus. You have isotopes, which, this is key, they have the same number of protons, because if you look at the periodic table, elements are divided by the proton count. They have the same number of electrons, but they're going to have different neutrons if they're different isotopes. So you can have a heavier element, you can have a heavier nitrogen element because it has more neutrons. And then you should know that for certain metals, it's going to have extra, or I should say it's going to have a lack of valence electrons or added electrons, so it's going to have technically a negative charge to it if it was to fill up all its orbitals. Light interacts with matter. You have the same thing I mentioned before. This is key. This is going to be absolutely on your test. I was told multiple times that you should not go through this course without knowing this. Why is our atmosphere blue? If you remember, it kind of goes back. It's not related to what I said earlier about a lunar eclipse being red, but it deals with that matter that the angle of scattering is so shallow that you get that red glow on the moon. Well, in this case, for atmosphere being blue, your scattering effect is not is at such an angle where the blue wavelength scatters most easily, and since it's going to be scattering multiple times within the atmosphere, the light that eventually makes it to your eye is going to be overwhelmingly blue. So then we have the Bohr model. You have energies at discrete orbitals, so you have the way we visually understand this is different distances from the nucleus. And based upon how we put the distances, would basically be the number, how far away energy is. Also remember that the energy is not in joules necessarily. It's called EVs, electron volts. And this is just your comparison. So if you see an EV, of course, just remember it is a joule, but it's a unit that is used for conversion purposes to make things easier in terms of magnitude. Let's see. And this is also important because astronomy is based on not only seeing what we can visually see, but understanding that what stars or planets are made of, and it's based upon the spectrum. What gets absorbed, what is emitted, as we take in light from the universe. Okay, finally, we have the end of chapter 5, because chapter 6 was like telescopes or something like that, and that was not going to be on the exam, I was told. So no telescopes, so this is our last brief slide. Temperature, you have your black body spectrum. Black body, the black means that all wavelengths are present, even though black means all wavelengths are technically absorbed, and you can't see. That's why things look black, is because no light is reflected. But they call it a black body spectrum because because it's going to have every single wavelength like black does. Black absorbs every wavelength, so a black body spectrum is all the wavelengths. However, as you go along at different temperatures, you're going to have different intensities of a given wavelength. Let me say that again. At different temperatures, you're going to have different intensities for that given wavelength. I saw that was in the notes, so please make sure you have it for the test. It will help you out as well. Then you have the power per unit area definition. It's proportional to the temperature to the fourth power. You have your peak of emission moves to shorter lambda as temperature increases. I think this is a connection from this first statement, that your peak of emission moves to shorter lambda, lambda being your wavelength. So something that is blue in wavelength is actually going to be hotter than red because there's more energy. So something that actually has more energy has a shorter wavelength, blue, and will be hotter than red. And then I also briefly saw that there were some Kirchhoff laws. So a continuous spectrum is all possible wavelengths have some type of intensity. Just a spectrum means that you're going to have some zero intensities at certain wavelengths, so you only will get some peaks as you go along the wavelength and on the bottom of a axis. And then low density gas will actually select certain energies, and it will, I think we'll see that when we go over the test after this. And then finally, you should know the Doppler effect, and you should be able to calculate, there's an equation in the notes for calculating shifts. So if a given wavelength is measured, maybe you want to know what the actual wavelength was at a star or at a planet when it left, there's a way to calculate that. So that ends the very brief overview of however many weeks we've had astronomy. Any questions from anyone online? Hopefully I didn't put you to sleep. Sorry. Any questions about anything? Any problems with anything? Any struggles? About what? Yeah. So in physics, we like to keep things easy sometimes with frictionless surfaces, right? So if something's moving along a frictionless surface, we ignore friction. However, if that were the case on a sphere, it'd be kind of like one of those cool, kind of one of those orbs that has the water in it, and if you just kind of turn your hand, you see the liquid move in the direction you're turning it. Well, the fact that it even moves at all is because there's that, it's called a viscous, the water's viscous a little bit, or it has some kind of friction on the outer edge of the glass or whatever. So if you think of the orb as Earth, as the Earth moves, not necessarily on the outer surface now, because that's not where the water's touching, right? The water's touching necessarily the inner. So if it's touching the inner, as the Earth moves, it's actually creating a slight shift of the water itself, which also plays, I guess, a small role with determining exactly how high or how low tide is. Because remember, it's a three-dimensional thing, so they try to make it like a cross section. So they say if the moon is here, here, or here, you can kind of see the water expand. They can do a dramatic effect. However, because the water is actually being pulled by the Earth's rotation too, it's going to diminish it, I think, a little bit. It's going to diminish the effects of the force pulling, because now you have another component of force in a sense. You have a frictional force. Does that make more sense? So it's kind of like there's a space in the water. It's the land. Okay, it's the land touching the water, and the farther away you go, you get this kind of effect. So if you're really close, the water, I believe, is moving with the Earth, but even still, you're in a good radius direction in the middle, right? Because the core, I forget, the Earth's thrust is only 1% of the total radius or something like that. So the water depth might go maybe, I just telegraphing, but maybe 2%, right? So even then, you're still at a very far enough way that the radial effects can be probably calculated with the friction. What exactly do you remember her saying about it?
Well, that's I know she had a good diagram of the moon going on Earth right then, like except the shifting water further up the moon. And then also on the opposite side of the planet, the water was coming out from the opposite side of the planet.
Yeah, that's why I briefly mentioned that if you happen to be reading a book that the sun has its own force effect, the moon, of course, has a greater effect, but then the actual spin is like a third measure long. So it's like you can't just say sun, moon, that's it. The water is, you can't say, I guess, all the water is moving with the earth or the water's still. So it's like one of those finite assumptions that you shouldn't make. And of course, they mention it because it's not infinitely small, but that it's typical. Other questions? Yes, because longitude, latitude, latitude. Yes, because latitude is altitude is a measurement of distance from the Earth's crust to a section of the atmosphere in a radial direction from the Earth, a radial direction, and latitude is a radial, an angular displacement, looking at a kind of celestial sphere from a origin standpoint. So altitude is a radial direction, like a line, and the latitude is an angular displacement. And then when you, of course, use two angles, you can find the spot on Earth for longitude and latitude. Precession of. So the question was, why does the Earth's axis kind of spin around? What is it? What is it? Why does the Earth's axis precess? Okay, so precession doesn't change the angle. I'm just going to start there. Doesn't change the angle. But it has to do with any kind of rotation dynamics for calculating. Um, with the rotation, there's an added force. Usually with rotation, it's the force is torque, because there's really no counter force to the torque. The Earth is going to rotate itself. The axis is going to reset. So it's kind of like, again, almost back to Newton's third laws. There's no counter force to keep it from not precessing. So the book just says it does, it happens, and it's just a matter of rotation. A further, more detailed explanation, I would say, is there's really no counter force. fact that it's already tilted in its orientation, it's saying that because it's not a perfect sphere and your center of mass is slightly off, as the center of mass tries to move, in a sense, because it's rotating, that's what's making, because it's not a perfect sphere. So if it was a perfect sphere, the center of mass would always be in the same place as everything was affecting it, and it would not want to try to alter its situation. However, because it's not, the center of mass is slightly off from where we would want it to be perfect. And if you were to look up kind of that idea, why the center of mass with wobbling objects want to change, that'll probably give you your best answer of why your precession changes, because it has to do with the center of mass idea. Hi, Anders. You should be able to. I was just talking to Maxwell, who is no longer on, it looks like, and I was saying that you can. I'm just not sure how quickly it's going to be online for you to download. I'm going to be giving this information to my boss to put up on the ARC website, so that it'll be like a kind of like a review link where you can download this stuff. However, I know your test is tomorrow, so I don't know how quickly it's going to happen. Two major reasons. One, I'm giving it to my boss, which shouldn't take much time, but then it has to go through IIT's administrative, like authoritative administration, and then they have to kind of okay anything that goes up on their websites, and I don't know how quickly that's going to happen. I can see what I can do. Thank you. Okay, so we have 1 hour left. Were you given like an exam or a practice exam? Good. So I have a practice exam also for those online. And I hope to just kind of go through it in the hour we have left and kind of explain the do's and don'ts for a problem. Okay. So it looks like you're going to have a true and false section. And with every true and false and with every question, you should always be careful about the exact wording. For example, as we can see in number 1, Earth is always precisely 1 AU from the sun. No, I went over that. It's actually on average 1 AU, false. It's possible to view the moon in the first quarter phase the day after a total lunar eclipse. So the two key things here, which are written, is that total lunar eclipse happens during a full moon. Okay, so that's kind of where your diagram comes into play, and knowing eclipses. These questions are going to have to make the fact that you need to know 2 or 3 pieces of information before you move on to answer it, which is pretty obvious right here. So it's during the full moon, and we know that you can't really change, in a sense, anyway. You can't go from one phase of the moon, which we should know happens, to another phase in a day. So you should also know that can't be possible. Kind of knowing the basic idea of the eclipses too. So when energy is converted to one form or another, a tiny amount is lost. No, you might say it's lost to heat. You might get a half credit if you write that down, but heat is an energy, so the total energy is not lost, so false. Escape velocity from Earth is greater for larger masses, basically. It actually ends up the velocity to escape the Earth. Only depends on the mass of the planet or the star. Trying to escape a star or a black hole, right? The mass of the black hole. Right? This comes from isotopes. Right, so if you have the same element on a periodic table, it's always going to have that atomic number, which is the number of photons. Any object moving relative to Earth will have a Doppler shift. So any object moving relative to Earth will have a Doppler shift when viewed from Earth. So say we're watching a star or a planet and it moves across the sky. We're expecting a Doppler shift. This is not the case. If you have light, as it was said in your notes, moving left to right of you or on an arc, there's going to be no Doppler shift because it has to be light moving at a velocity towards you or away from you. That would change the wavelength. For example, as was drawn, she drew kind of like just like a light bulb. And she was saying that the waves get bunched up more as the velocity is coming toward you, and then the waves get bigger. It's the same principle. You have your wavelength, and this wavelength is either going to get shorter or longer if the whole system, either the whole system started moving faster, because this could be on an ambulance or something, right? Or a train or anything. Or if you start moving towards the object. So if you're watching an ambulance, because that's sound, but if you're looking at light, sound, light, not really the same thing, but same principle. If you're watching it go by you, it does change pitches, but that's because the actual distance from you to the object is changing as well. But if you just had an object, if you were only dealing with 2 dimensions, or even 1 dimension, only because, okay, so it's a little bit, I don't want to confuse even more, but if you're watching something from afar and it's moving with that velocity, technically if you were to view it over here, the distance to you is changing because this is a wavelength, and as it goes even the slight angle, the wavelength has to change for it to be the same object. So if it's always going to be the same frequency of pitch being shouted at you, or the same light, if you can calculate this angle, it's going to be a different wavelength. However, because we're dealing with what, arc seconds, even maybe an arc minute sometimes with some planets, this angle is so small that we're actually like dealing with super close objects in terms of the angle. So that's why if the object is moving in the night sky in a circular pattern, it really doesn't change the radius it is away from you. So the radius here and the radius here are the same distance away from you, and therefore the wavelength that it takes to travel to you is going to be unchanged by any velocity. If it's traveling right on this arc. Okay, so this is, of course, why I put it on the PowerPoint is the cosmic address. Just know the sizes. You should know why we have seasons. That's probably going to be on the test. It's a very important reason. Which of the following statements is true? So this is knowing your definition. So you should know what an equinox is and what a solstice is. An equinox is where the northern and southern hemisphere are kind of in a vertical line in number compared to the Earth. So one hemisphere is not farther or closer. I mean, it relates to certain days of the year, but those days of the year have temperatures, right? Summer, winter, fall, spring. So an equinox is going to be your fall and spring. And let's see, part C. And then you have to remember that the solstice, depending on if it's winter or summer, will determine if it's farther or closer away. Ecliptic plane we went over. This one was backwards. It's the plane of Earth's, it's the plane of Earth's orbit around the sun. So even though we're looking at a celestial sphere, and we're mapping the Earth's position on the sphere relative to Earth, it's actually the Earth's orbit, we're actually going slightly above the sun and slightly below the sun. Even though on a celestial sphere, the sun goes above and below our equator. If we're looking at from what the sun sees, in a sense, the Earth goes slightly above its equator and slightly below its equator. What is the ecliptic? Now that goes back to the celestial sphere. It's the sun's path. So this is kind of like, there's of course going to be questions where it's not exactly maybe easy to cancel out all of them if you don't know what you're doing, like you don't remember definitions. So which of the following statements about the celestial equator, remember it's the Earth's equator, is true at all latitudes? If you go through all of these. So this number D isn't true. Letter D isn't true because you can change your horizon. And even though this is true, the statement itself is true. It has nothing to do with this question. Now we're getting to our history section of things. For most of history, the lack of observable stellar paradox was interpreted to mean that the fact that they could not measure such small angles, remember I said, was the fact that they chose answer number 2. They couldn't measure small angles with the naked eye, so they said, well, we can't believe stars are millions of miles away or millions of kilometers away, so therefore we have to have Earth as the center. They had 2 options. They could have said Earth is not the center, but we would have seen our sphere in our center move closer to our celestial sphere, and we could measure things differently. But they could not understand. Why could they not detect it? Remember, you got to know what a stellar parallax is. So here we go. Here's retrograde motion. And this question takes into the fact that we are moving counterclockwise. And so that means that we actually see stars move eastward. So what causes it? Is when, let's see, why is this one? Turbulence in Earth's atmosphere. That has nothing to do with it, because remember this retrograde motion happens over the course of weeks at times. So the fact that you can have turbulence over the course of weeks is kind of negating it, because these guys are smart. They try to measure stuff during clear nights when there was no turbulence, and they still measured the same thing. So if something moves slower and it doesn't move faster, the reason why that is wrong is from the fact that I was trying to explain that as you move, both objects are moving in a sense the same direction. It's just a matter of how you view it, so it doesn't matter in speed. The stars do not shift. Let's see what other things we have to do. So this was the exam from fall 2012, so that's what, a year and a half ago. So some things she might have just mentioned in her notes too, unfortunately, and it could be a point off or however many points the question is too, because she could have just mentioned, we have all these planets and this one moves the slowest. So you got to make sure you remember some of the smaller details, unfortunately. Any questions from online? Everyone doing okay? This has to do with space point. So again, the celestial sphere makes up kind of a foundation for many things. Where are you on the planet? In this case, where are you in orbit? So if we're on the other side of the sun, and the sun is going to be in the daytime, when we're trying to view the star, we're not going to see it because the sun's in the way. So this idea of the celestial sphere and the fact that that sphere, inside the sphere, you can have the sun moving around the planet for a day, will block out certain views of the stars. Remember, lunar phases happen about 29 and a half days, about a month. So it's possible that if you have a long enough month, you actually could get the same phase because you have to be longer than 29 and a half days. So what January has 31 days in it, 30 days. So you're able, 31 days, so you're able to get that extra phase in there, is what this is talking about. And the reason you should have that moon diagram in your notes is because she is not going to exactly have those times written down. So if you can at least quickly find on your diagram what moon she's talking about, you can determine how many weeks or how much time passes between phases, or how these things work together. Because now we're talking about if the moon rises around 3 a.m., you need to know in your diagram, okay, where's 3 a.m. for rise? And then you can find its phase quite easily from the diagram. It's an open note test, I suppose. So we're kind of taking our note-taking abilities into practice here. You see a crescent moon sitting after the sun sets. Okay, so this one's a little, not really backwards, but with your diagram, the sun sets. Okay, well, you should know what time the sun sets, and then you can figure out, okay, the moon is going to set after that time on your diagram. And I believe they have it so that the new moon is up when the sun is up. The same hours the sun is up is when a new moon is up. So therefore you can, that's kind of where the logic is in this one, is that the sun is up at the same time as a certain phase of the moon. So then you have your solar eclipse. And I briefly mentioned this, the nodes. I briefly mentioned the nodes. I briefly mentioned the phases of the moon. So new is for solar, and I can't remember what I put for lunar. You should know those. Okay, so when it's a full, when the phase is full, that's lunar. When the phase is new, that's solar again. You should know what each of those models were. And so with any given model, remember I went through all the scientists, and all the scientists had made slight changes to the model. So again, you're going to have to know exactly what each model consisted of, because she can trick you with this one by saying 7 perfect spheres. So the wording, it's a multiple choice test, so the wordings are very critical to your answers. I guess as an overall idea for multiple choice tests is go with your first initial guess or your first gut instinct. Because the more I'm not very good with English language even though I'm a U.S. citizen and grew up with it, like, the more you read something, the more you're going to confuse yourself, the more you're going to get tripped up on how words mean what they mean. So read it slowly, read it through the first time. You know, I usually skim, when I take tests, I skim, so just be sure to read things, because you might miss a word. We don't want you guys to make mistakes, or girls. Again, retrograde motion, how did he explain it? You should know his model. And then this is another scientist I mentioned. You should the Ptolemaic model, the Ptolemaic model you should know. Another scientist I mentioned. Trying to think about why stuff was good. So I think I mentioned there was like 5 models. I think there were the Earth-centered one, and then there was the Ptolemaic model, and then we have Ptolemaios. Can't say that. We had his model, and then we had the gentleman after him, the start with a T, his model, and then we had Kepler's model, and then I think Galileo gave a model, but he basically proved that the Earth is no longer the center. With his discoveries of, I think, the moons of Jupiter and the face of Venus. So, right, okay, so we have Tycho, Galileo, PHYS, Kepler, Ptolemy, and can't remember who did the very first geocentric model. And Kepler developed ellipses, which were able to, for I think 50 to 70, I think it was 70 years or so. So a very long time, his elliptic model was able to predict every known star or planet that they had found to that extent. So you should, she can ask you one of these, where you're in your notes, you're going to have all 3 laws, and now you have to do like a, which one does not fit. So now we have to remember that Newton, we need to remember that Kepler dealt with just the motion. Kepler did not do, okay, let me put it this way. The first person to do forces was Newton. Kepler was the first person to find that there was maybe a force between objects in space, but it was Newton who actually developed and formulated an equation to predict the forces between objects. So Kepler dealt with motions, Isaac Newton dealt with forces. And as you can, I mean, I'm going a little bit quickly, but that's kind of my choice. But as you can kind of been seeing, she hasn't, at least for this exam, she hasn't put questions out of order. So she hasn't asked you any chapter 5 questions first. That's what I mean. She hasn't asked like light or anything like that necessarily first. So she's kind of, at least in this exam, she's nicely just going through the chapters in an orderly fashion. So it's kind of nice. That way you don't have to think, okay, where am I on my 5 chapters? You can kind of say, oh. So I'm not going to say that's how the test is, but if it seems that's what the test is doing, that's kind of a nice idea of where you should be in your knowledge bank on your notes. Okay, I mentioned this several times. Which observation offered direct proof of planet orbiting the sun, meaning Earth orbiting the sun, the phases of Venus, or the result was they changed Earth to orbiting the sun, but the fact that Venus had phases meant all planets are now orbiting, and they went on to prove it with some other visual. So, yeah, so this one's confusing because the 4 moons of Jupiter was not direct proof. 4 moons of Jupiter, all that meant was saying that just because our planet has a moon rotating around it does not mean we are the center anymore. However, the final nail in the coffin, the final absolute proof is this letter B. This was kind of the preemptive strike, if you want to call it that. Okay, so I mentioned angular momentum. There was a question on this exam about it. So hence, just make sure you know where it is. You have it written down. So, do you guys have any questions? Like, I know I'm going through it, but it's thankfully it's very structured, so she's done a very good job of structuring it. Online, any questions? Can you guys still hear me okay? My voice is a little raspy, so I'm not sure if I'm cutting in and out. Thank you. Okay, so here's just another word. So for force of gravity not dependent on distance between objects, that means your distance cannot be in the equation at all. That's not the case. Inversely proportional to the distance between objects, that means it's 1 over r, or d, 1 over d, sorry, not 1 over d squared, which is the correct answer. So you got to make sure that the square's in there. Directly proportional means that the distance would be in the numerator. It's not the case. Directly proportional to the square means it's the d squared is in the numerator. That's not the case. So you should know how to understand these math terms: proportional, directly proportional, inversely proportional. So here she put the math out for the answer. If I double each of these if we double each of these masses, 2 times 2 is 4. Because it's in the numerator, this answer is going to increase by 4. It would decrease by a factor of 4 if we did something to the denominator. Okay, so here's a lunar phase tide question. Again, this is why I tell you to probably put the diagram, find it in your notes if it's not there. Also for the gentleman in the back of the classroom. I think, did she draw a picture you said about this?
Yeah, it was over here.
Did she have multiple moons around it? Good, because that means if it was the new or full or new moon is when the tide effects occurred, then the least pronounced would be first and third quarters. Right? So it's kind of like one of the things that might not be directly on your notes, but you should have something there because then you can do the deduction, okay, what's not there? That's going to tell me the exact opposite. So number 33, as you can see, we're just about halfway through the test. This has to deal with Newton's third law, number 33. The force on the star is much smaller than the force on the planet. The forces are equal. Newton's third law says that every force has an equal and opposite reaction force. Well, the force that the sun applies to Earth has to be the same force that Earth applies to Sun. However, as we can see in Part B, the accelerations are going to change. And that can be seen here. We set the forces equal to each other. This side is the force of the planet. This side is the force of the sun or the star. And if the masses are different, the accelerations have to be different. Hence why you don't really think about the sun. We think about us orbiting the sun rather than the sun orbiting us, because we're moving, even though we're both moving in a sense at the same acceleration, or either way we think about it, the acceleration is the same. However, the sun is also moving in its own elliptical pattern, or whatever the pattern of the sun is in the universe. Newton's third law is now brought up in question 33, so that means we're in about chapter 4, right here. And here the question is just going to trick you because it has total orbital energy. You don't need to even worry about the orbital part. Total energy. So if we're talking about the total energy, whatever the energy it had is always going to be what it has. It's going to be changing. The parts of the total energy are going to be changing, but the actual total energy, of course, conservation is going to be the same. Okay, everyone pay attention. This is the other equation you're going to probably need to know and find in your notes when you start comparing periods and distances. This is, I know this is Kepler's third law, but now we're applying Newton's laws to it. And hence you get the proportionality constant, which is the 4 pi squared over g, and which is the mass of the star. I think I was looking through the notes, she wrote this down several times, so just be familiar where it is and how to read it. Again, as we increase m, this whole constant goes smaller. And if this constant goes smaller than 1, let's say our starting was 1, right? If m of our sun was plugged in here, this would be 1, or whatever this number is. But as the mass gets bigger, this number is going to go smaller than the previous number, which then means if you were to compare the two, we would get a shorter period. These are your other equations you should know. So Kepler's third law, I think, was written down in equation form. We're into chapter 5 now with energies and frequencies. She never, I don't think, wrote out the actual equation for energy and wavelength, but just knowing that it's inversely proportional should tell you that if we increase the wavelength, we're going to get a lower energy. And if we increase the wavelength, we're going to get a lower frequency, because frequency is also inversely proportional to wavelength. So why is the Earth's daytime so blue? Absolute question on test. Easy points. So how, do you guys feel okay with like absorption of electrons or absorption of energies for elements based on what you were saying? Because I know that can be not really tricky, but if it's gone too fast and you don't try to understand it. So I don't know, did you go over it well, you think, in the class? Or? Okay. So you don't know the type of wavelength produced for 38. So you can't say radio waves or X-rays because those have a specific wavelength associated to them. So you can't know exactly which one. When electrons fall back to lower energies, to fall down, they have to release their energy, emit their energy, the emission line spectrum. Thermal radiation, hopefully you won't have any trouble with that, but that kind of deals with at a given temperature, what is the total black body spectrum look like? Remember, it changes as you change temperature, so that's kind of what thermal radiation is talking about. And of course, it's not absorption because we said emission. This was briefly mentioned, so this is kind of like, I believe, a hit or miss question. When she was talking about gases, she mentioned like dense, full liquids, and then she went into thin. So remember, a black body thermal emitter produces a continuous spectrum, meaning at every single wavelength, you're going to find some type of intensity, even though it might be really small. For certain gases, in this case a hot thin one, you're actually not going to get all the wavelengths having intensity. You're only going to get gaps of wavelengths with certain intensities. And I believe that was shown in your notes too. Any questions from my mind? So remember, the higher the temperature, well, actually, she did a calculation here, which is why you should probably know where that is. But this is where I told you to remember where the electromagnetic spectrum was, because you can then look up quite easily for a wavelength of this size, what is it? This deals with the red and blue stars. I mentioned that in the PowerPoint, how how blue is hotter because it has a smaller wavelength, and red is cooler because it has a longer wavelength. This one I didn't touch upon in the PowerPoint, but it is in your notes. It's like the last page of your notes, so please look over that. This was also done. I didn't go over this in the PowerPoint, but this is in your notes. So which of the following conditions leads to an absorption line spectrum from a cloud of gas in your stellar space? The fact that the cloud is cool means that it's at a lower temperature than the incoming wavelengths. If it's cooler than the incoming wavelengths, that means it can gain energy and become hotter. If it gains energy, that means it's going to take some of those wavelengths and absorb them, which is good because we're talking about absorption. And the fact that it's cool means that the star has to be hotter. This goes back to this equation right here. putting this up longer so people can look at it longer. Because I don't want them just to see why this one's right, but give them time to read the other ones, which is what I was doing. This goes into the describing atom size, not sizes, but the isotopes of an atom. And if you were to go through each one of these, you would notice something critical. So in this one, 8 protons, 8 protons, 8 neutrons, 8 neutrons. Oh, the electrons are different. It's not the same because it has different electron count. 4 protons, 5 protons, definitely different. 6 protons, 7 protons, definitely different. And this one is 7, 7, 8, 7, which is fine because the neutrons can be different for isotopes. And good, it has the same number of neutrons. I hope this is in your notes. I know it's true because I took an astrophysics course and I saw the math to why it's true, but I don't remember seeing it in your notes. So when we see the spectrum of a star, so the emission absorption lines, which one is not true? Well, we can tell how fast it's moving because of the Doppler shift. We can tell because of its highest intensity peak how hot it is. When you get a database, you can tell exactly what specific spectrum is falling, what elements are inside the star. But you can't tell necessarily from a spectrum the radius of the star. I think you need 1 or 2 other variables just out of curiosity, but it's not directly from the spectrum. There will be a short answer. Don't overthink it, is what I got from, I'm sorry, okay, so short answer, paragraph. Don't overthink it. I'll get to that in a moment. And then there's another short answer, kind of like a true-false, but it looks like in this case you have a table. So the absorption lines, right? So which transition represents an electron that absorbs a photon with this much energy? Well, if it absorbs that much energy, it's going to go from its ground state, wherever that is, well, we labeled it as 0, to a state of 10.2 electron volts. The only one that does that is B, as seen here. Which transition represents the electron that emits a photon with the highest energy? So now we're dealing with emission, which means our arrows cannot go up. So we only have 2 that go down. Of the 2 that go down, one goes down the gap of 10.2, while the other one goes down the gap of 12.1, hence A. Which transition represents an electron that is breaking free of the atom? As you can see up here, maybe you talked about it, the ionization energy is the amount of energy it takes to break away an electron from the nucleus. Knowing that, as you can see, the energy that it goes to is somewhere above this ionization energy, so therefore it's actually breaking away or breaking free of the atom. So that would be E. transition is shown is not possible. You only have specific energy levels. There is no energy level here. There is no way an electron can go here. It's just not possible. It's kind of like one of the cool things about why technology works and why electrons are so mysterious in the first place, is the fact that even though an electron is a particle, it can only absorb a certain amount of energy in its lattice or in its structure for it to go up to the next level. So it can do any number of things. It can go all the way up here and then go down, up, down, and then go back down. So it can do kind of chaotic looking things, but it has to jump to these levels. So the fact that it's jumping somewhere here is actually, it's never observed, first of all. And I think mathematically it's not possible either. They've done mathematic things with the hydrogen atom, which of course has one electron. You can measure stuff for one electron and where it is. It's observed. It's never observed in anywhere else other than at specific energies. And based on quantum mechanics, I think this says that to you. But I'll let you read that to kind of get an idea. This one I was reading, and I think it's hard, only because I spent 2 days understanding your astronomy. So I would not know where these are on a map. I would not, like, I just average geography. I wouldn't know what New Guinea is and Stonehenge, England is. So I wouldn't know, like, would that be on the opposite horizons of my celestial sphere, like, so if I see the moon on one side, would it take half a day to get to the other side or anything like that, or would it shift slightly? But she kind of explains it. It's based on the moon, earth, sun angle, remember, is just what phase it is in. So if it's directly in the same angle as the sun, it's the new moon, I believe. You can't see it. It's daylight. You can't see the sun. And then I'm not sure if it's clockwise or counterclockwise if you want to get the angle. But depending on which angle you go, you're going to get your different phases. You're going to get your third quarter, your first quarter, your full moon, and then all the waning gibbous, waxing gibbous, waning, all those in between. So she was saying in the new moon, angle 0, and then there's her answer for you. So the assumption here is that, or not assumption, bad word to use, but the fact is that no matter where you are on the Earth, the moon is actually in the same phase everywhere. It's just a matter of abstractly thinking where you are on Earth, I suppose. But no matter where you are, the moon is always going to be in the same place relative to the sun, is what I'm trying to say. The moon is always going to be in the same place everywhere on Earth relative to the sun. So if you're in a different horizon, or the half sphere, you can't see the moon for whatever reason, well, it's still at the same angle in each lane like the sun, even if you can't physically see it. So that's where you gotta just make that Oh yeah. Right, that's what when I first read it. Because she does, unfortunately, right? It says
Yeah, just
on what date closest to that date will be the right time. And so it's kind of like a counterproductive. You're saying, well, it doesn't matter as long as you're within maybe what, a day, half a day. So it looks like she doesn't want like an overzealous answer. And what I mean by overzealous, also if he goes online, is maybe let's see if there's I know some people have really fine handwriting print, and when you start getting fine handwriting print, you're able to put a good 3 paragraphs in this space. So I guess condense your words too is a good thing to do as you grow older, to learn how to say things. Like for me, I was rambling in this review a little bit sometimes, so but just try to condense your words into the most concise way of saying things as possible. Does anyone online need me to show the question again for the last question? Okay, so it is now 7:51, so I'm open to any comments or concerns on the exam whatsoever. It kind of helps with her exam that I just showed you too, so you get an idea. You get an idea of what she's doing, thankfully, so you're not going to, so I'm not expecting too many questions. But this
there to be short answer.
sort of. There was one that was like a paragraph, and then there was one that was more like, I forget what they used to call them, but when I had them, they would have like, I always used to take like line A and like B and then draw a line to it, but instead of taking the letter and plugging in the letter. So it's like multiple choice again. You have like 5 answers. And so you got to pick one. But yeah, they used to have tests where you could draw the line. You have a chaotic mess of line. Yeah, like matching. So that was her year and a half ago test. I can't imagine she changed it too dramatically. So again, this was put on by the ARC, as requested. My name is Daryl Montanaro again. I am a grad student at the ARC, and I do have my undergraduate in physics. So if that was a concern of anybody. A little bit about me. You are free to go. For the 3 people in class though, I just need your name and A number on the sheet over here, because that's how we kind of record you were here. Everyone online, I think you were automatically recorded because you had to sign in somehow. If you're not, don't worry about it. We'll work it out. I'll work it out with my boss on how to fix that for the future. But for the students in class, just remember to do that before you leave. But I'll be here till 8. Thank you. Yep. Have a good week and rest of it.
Not too fast. All right, see you in a minute.
Thank you. Anyone on, or do we have people online still? It looks like I see people, but I don't know if it keeps you logged on. Any questions, concerns? Do you have a question, Anders? Okay. Yeah, I don't know what she's doing for you. I heard the notes were online, so it wouldn't be a bad idea, to have them, print them. Um, you know, I know the book. It's a pretty good sized book, so I know it wouldn't surprise me if you didn't buy it, or who did buy it. But she did follow the chapters in the book very closely. Um, there wasn't really anything left out of her notes, and she of course supplemented her notes. But because it's a multiple choice exam, you're going to have to read the questions carefully, and for several of the questions on the old midterm, you kind of had to know things to answer it, like vocab or exactly the phases of the moon. Um, so, I believe, like new moon is when the sun is up, full moon is on the complete opposite side of the sun. Um, and then it wanes, and then you have to know the waning and waxing, the gibbous, the crescents. Chapter 5, the last chapter you guys went over, was a good meaty chapter. So it's almost like in terms of the amount of material that happened on 1, 2, and maybe half of 3, it's probably like 5. There's just a good amount of information. And as you can kind of notice, I'll say it again on the test, the old midterm, it kind of was very chronically ordered, in chronological order. So it kind of helps you, I guess, if you have your notes in front of you, it should help, maybe if you take a quick glance at the test when you have it, to kind of figure stuff out. It was, I think it was about a little over it was like 35 questions, 32 of which were multiple choice, give or take the true false, sorry. So that means that's what, if you have an hour and let's say 15, but maybe she'll give you some extra time. I don't know how strict she is, but you can do the math. That's about, 60 minutes divided by 30 questions. That's about 2 minutes a question. And it is hard because because you have to read every answer for some of those. So that's kind of why I guess I could also suggest it's important to read the actual question carefully and know what you're looking for. The very basic example is the isotopes. And when you deal with the isotopes, you don't need to read every question all the way through. You can do, a quick glance to figure stuff out. So I think from most of what at least I went over, there was maybe like 1 or 2 questions on the old practice exam that weren't exactly specified, which isn't too bad, right? You should definitely get a passing grade on this test. It is 8 p.m. Is there any last minute questions? I see 3 participants still online. Is there anything last minute? Otherwise, I'm going to end the session. Well, study hard. Hope it goes well. Don't stay up all night.